Polarizing angle. So we're talking about polarization by reflection. A beam of unpolarized sunlight strikes the vertical plastic wall of a water tank at an unknown angle. Some of the light reflects from the wall and enters the water. The refractive index of the plastic wall is 1.61. If the light that has been reflected from the wall into the water is observed to be completely polarized, what angle does this beam make with the normal inside the water? So the incoming light that gets reflected from the plastic wall air interface is completely polarized. It's reflected from the wall into the water with complete polarization. So that means the incoming light made an angle with respect to the normal of the plastic air interface, the polarizing angle theta p, and when it was reflected, the refracted portion of the light into the plastic made an angle 90 degrees with respect to the reflected light, and the index of refraction of plastic is 1.61. Okay, so the light incident on the plastic air interface makes the polarizing angle theta p with the normal axis. Okay, so the reflected and refracted beam should make a 90-degree angle, so that this is the Brewster's angle. The reflected and the refracted light make a 90-degree angle for complete polarization, and using Snell's law at this interface, we can write the air index of refraction 1 sine theta polarizing is equal to 1.61 index of refraction of the plastic sine theta of the refracted light. So we know that the refracted light angle theta r plus 90 plus theta b p, this should add up to 180 degrees. So theta r plus 90 degrees plus theta p should be 180 degrees. So the refracted light makes an angle 90 degrees minus the polarizing angle. So we can write sine theta polarizing is equal to 1.61 sine 90 degrees minus theta polarizing. Sine 90 minus theta is cosine theta, so this is 1.61 cosine theta polarizing. So tangent theta polarizing is then 1.61. Sine theta divided by cosine theta is 1.61, and we find the polarizing angle as tangent inverse of 1.61, which is 58.15 degrees. Now this light that gets reflected from this interface is incident on the air-water interface and gets refracted in water. So the index of refraction in water is 1.33. So this is n equals 1.33. And now we need to find with which angle does it strike this interface. Well, this angle is polarizing angle. This is 90 degrees, so this is making an angle 90 minus theta polarizing. Okay, so if we write Snell's law at air-water interface, the light reflected from the plastic surface is in the air medium, so index of refraction 1, sine of 90 minus theta polarizing, that's the angle with which it strikes the surface with respect to the normal, is equal to index of refraction in water 1.33 times sine theta x, where theta x is the angle the light inside the water makes with respect to the normal. So we find that sine of 90 minus theta p we found 58.15, so this is 31.85 degrees, is equal to 1.33 sine theta x. So theta x is sine inverse sine 31.85 degrees divided by 1.33, and this gives us an angle theta x equals 23.4 degrees. Okay, so that's what we were supposed to find. What angle does this beam make with the normal inside the water? Inside the water we have this refracted beam, so that's the angle it makes with respect to the normal. Okay, so we have a beam of unpolarized light striking the vertical plastic wall of a water tank at an unknown angle, but then we find that the light that has been reflected from the wall into the water is observed to be completely polarized. So this angle is the polarizing angle. So we have theta p, and 1 sine theta p is equal to 1.61 sine theta r, such that the refracted beam in the plastic makes an angle of 90 degrees with respect to the reflected beam. So theta p plus 90 plus theta r is equal to 180 degrees. So we have theta r is 90 minus theta p. Therefore, sine theta p is equal to 1.61 sine 90 minus theta p. 1.61 is the index of refraction of the plastic wall. So this is 1.61 cosine theta p. So tangent theta p is 1.61. Therefore, we find that theta p is tangent inverse 1.61, 58.15 degrees. And Snell's law at the air-water interface gives us an angle of 90 minus theta p for the incoming light from, that's the light reflected from the plastic air interface hitting the air-water interface. And so we have 1 sine 90 minus theta p is 1.33 sine theta x, so sine 31.85 is 1.33 sine theta x. So theta x is sine inverse of this, which is 23.4 degrees. Now, in the lecture, we have defined this polarizing angle not with respect to the normal, but with respect to the surface. So as long as you define it in the proper way and you know that you have a 90-degree angle with respect to the reflected light for the refracted beam, you will be okay. So if you define this angle to be the polarizing angle, then you see that tangent theta p is equal to the index of refraction of the plastic wall divided by the index of refraction of air, which is 1. So going with Snell's law at all of these interfaces and making sure that you define the angles properly, you will get the right answer. And using the geometry here, you have to be careful with finding the exact angle each beam of light makes with respect to the normal when incident on the interface.